welcome to the Inside EVs podcast and the fourth in a 10-part series of tech talks presented by AVL. Well, there's so much to learn about the exciting and dynamic field of EVs that when you want to go to someone to talk authoritatively and knowledgeably about this kind of technology, we wanted to go to a company like AVL. They work across many areas of electrification and with both startups and the world's biggest automakers. In this series, we've already looked at the various paths to electrification, how to simulate the various parts of a vehicle, and even how to develop a brand new car in a virtual environment. Well, coming up on future shows, we'll talk about charging technologies, but today we're talking about battery safety. EVs are already far safer than fossil cars, with things like the rate of fires far, far lower. But work doesn't stop, always trying to make them even safer. Welcome to today's expert guests. It's Juergen Schneider and Wenzel Prochazka from AVL. EVs are not a new thing. Electric vehicles were the first cars designed, really, before combustion cars took off. So this isn't new technology, even if the latest cars on the market are using cutting-edge technology. But if you can tell us briefly about how battery technology has changed along the way and over the years.
I think the first cars that come to my mind instantly are the cars out of the period of 1910. So at that time, we were driving around with e-motors. Yes, that's true, but the batteries were wooden boxes. They were lead acid in wooden boxes, and actually some similarities to lithium to lead acid today, but not too much of it. And when you look at electric vehicles today, you definitely see lithium-ion written all over it, and there's even some new ideas going to sodium-ion and other ion sorts, which is a completely different technology than lead acid was at the time. And so, in short, energy density went up through new materials, efficiency went up through electronic controls, and manufacturing accuracy that's possible today that was definitely not possible at the time.
If you go back to the early days, just a quick follow-up question, you go back to that early part of the century when electric vehicles came first, but then combustion cars arrived and took over for 100 years. Why was that? In terms of the battery technology? Was it just not good enough to compete with gasoline?
Difficult question to answer, to be honest. There is a lot of stories around what happened actually back then, which draws a picture of two competing technologies that were, in the end of the day, decided by some potent deliverers of oil and of other materials to burn in those vehicles. I think one of the shortcomings of the vehicles at the time was that when you go to bigger, especially to bigger vehicles, so commercial vehicles today, trucks, that was I think a bigger market at the time than personal vehicles or passenger cars. They could not deliver a very high load at an efficient range. The truck market was more influencing to the development of the technology than it was actually the pass car market or the shortcomings on the pass car market.
Some people would argue shortcomings still in 2020 because of just how good fossil fuels are at storing energy. So can you just talk us through perhaps the difference between stored energy in a battery and stored energy in a unit of fossil fuel, unit per unit? Batteries are catching up. So what's the current situation?
If you just say energy per stored unit, we have to look at the net heating value. So if you're burning the stuff, if you're burning a tank or a kilogram of diesel fuel, you get about 12 kilowatt hours out of that. If you're burning a kilogram of batteries, then you get 1.5 kilowatt hours out of it. But actually, you don't want to burn batteries. You want to use the electric energy stored in it. The electric energy stored in it is rather in the order of 0.2 kilowatt hours per kilogram, which is reversible stored. So that is what you can use every day, and you can use for a couple thousand cycles out of that. So we're talking a quite significant factor between 12 and 0.2.
And that stored energy inside a unit of fossil fuels, so much of it goes towards heat.
Yeah, I guess the efficiency is somewhere between, if you take a steady state number or if you take a driving cycle for a combustion engine, this is somewhere between 20 and 40%. what you can actually use when you burn it in the car versus the electric energy where you can use between 85 and 95%.
As a background to our conversation around battery cells and energy and things, when it gets cold outside, why can't I drive as far?
Especially, I think what was one of the differences also between fossil fuel and battery, the efficiency. So if you just can use 40% of the energy, there is the rest of the energy also used as heat, which you can directly use to heat up, let's say, the passenger cabin to, let's say, make the driver feel comfortable. And that's also something that you have to do separately with electric heating with a battery. So in this case, with the battery, cold conditions, there is no waste heat that you can use. And on the other side also, it's like the batteries, they all have also higher internal resistances. There's just less, let's say, ion flow, and consequently also there is less energy available. So we all know that from the mobile phones, when you have them outside in winter, it's just immediately dropping down the capacity. So that's the same effect also here for the cars, and you more or less have to heat up the battery here to be in the comfort operating zone.
And what is that zone where the batteries like to be?
I always say the battery is like a human being. It feels most comfortable between 20 and maximum 40 degrees. So if it's too cold, we don't work properly. If it's too hot, the same. The same is also valid for the battery. So if you feel comfortable, the battery feels comfortable.
When I was on a long motorway journey, so maybe it was going to be 4 or 5 degrees Celsius when I left the house, but I would get to work and the battery would be toasty warm. What causes that battery to heat up when I'm driving along?
Yeah, there are different, let's say, sources, but at the end of the day, it's always when you have some current flow through an electric system, it always will cause some energy losses, and this will be converted to heat. And the more, let's say, current you put through, there are higher ohmic losses, and that's typically then creating this heat up of all components, not only the battery, but also the cables and the let's say the electric components.
Recently, we've heard this phrase cell-to-pack technology. It seems like some sort of cutting-edge technology that's going to solve lots of problems with EVs. So can you just talk us through how batteries are made at the moment and perhaps what we might be going to?
So I guess batteries today, when you say modules and then pack, that is a very valid nomenclature that we use for the last 12 years in AVL battery development. And when I explain to people why we need a module, there's the technical reason, and there's commercial, supply chain, serviceability reasons. But if you look at the technical reasons, the module has to care for the needs of the cell. A cell is breathing by itself via the state of charge. A cell needs to be insulated from high voltage because its cannot insulate up to 1,000 volt. And it has to be electrically well connected. It has to be connected to cooling system while it's breathing and moving around. So the module basically cares for the needs of the cell, so the cell can survive inside the battery pack. And when you then look at what the pack does, that does the integration of the modules. Modules have fixed interfaces, mechanical connections, screws, plugs, whatever. And then you take multiple of those units and you put them into a pack, and there you put the safety around it, you put the vehicle integration into it, you put the electronic controls into it. So we have basically one inward-facing part, which is the module, and one outward-facing part, which is the pack. And now when you say cell-to-pack, that's been around quite a while, actually. Again, funnily, in commercial vehicles, where you had multiple sub-packs that were basically large modules, and you would put on a 8-meter bus, you would put 5, on a 12-meter bus, you would put 10 or so. And they were rather large cells and rather large modules or sub-packs. And this technology was taken to pass car from CATL last year, I guess, but the first time really in a big marketing push. And it describes basically that you make the battery housing care directly for the cells. which is not as easy as you might think, because moving around cells in a large stack of 1.5 meters, they could move up to 20, 30 centimeters if you don't compensate for that within the stack. So it makes design of a pack quite a bit more difficult on the one hand side. On the other hand side, it takes out a lot of parts, which saves cost, which is a positive thing if you want to go for mass production. And on the other hand side, once you have a failure inside one of those stacks, then you have to exchange the whole pack. So serviceability is going a little bit down probably.
I guess people would argue that EVs are pretty reliable.
I would completely support that, as most of the service incidents are actually electrical parts. So cells are not that high of a service incident. So that is why cell-to-pack technology is something that is a big discussion point in the industry currently.
Over the years, we've seen the newspaper articles or the internet articles of an electric car on fire. And that's understandable. That is understandable because new technology will always, by some people, not everyone, but some people will view it with skepticism, or they will worry. And so when there is a fire with an electric car, whether that's because of a crash or an incident, it tends to get reported more than a gasoline car, of which there are many, many fires every day. We've seen pictures of them. It seems to be quite quick, and we hear about this phrase, thermal runaway. Now, can you just explain to the listeners and myself, what is that? What happens when there is a worst case and when all of a sudden something's gone wrong?
The case that there's many more many more ICE cars burning than EV cars burning is just yesterday I had a newspaper article in Germany. 110 cars are burning per week and one EV. So it's quite a significant rate difference actually. On the other hand side, EVs are creating a nice fire blaze simply because they're burning at a quite high temperature on the one hand side, and they do have something which fuel cars don't have. They have their oxygen within them. So they don't need any additional air, or they don't need anything that you can take away from them to actually take the fire out. What happens in a thermal runaway? For some reason, one cell is destroyed. You can have an accident, or you can have a manufacturing defect, God beware. Then one cell is heated through a short circuit, and there's a lot of current flowing through a single spot. This spot is heating up until a certain temperature when in a conventional cell of today, the separator will melt, creating a larger short circuit. And then at some point, it will heat up so much that the cathode releases its oxygen. When this happens, the electrolyte starts to ignite together with this oxygen, and the cell starts burning inside, which then at some point creates so much hot gas that the cell opens and expulses parts of its electrode, and trying to heat the next cell and the next cell and so on, which is called the runaway then.
One important point here is also that when you have, let's say, a fuel tank, even let's say there is this worst case that the fire starts to catch really also the tank, there's a big explosion, and due to this detonation, you probably will release a lot of, let's say, liquid fuel into the environment, but then the energy is gone. So it will not evaporate, it will probably be spread around, and the energy is distributed and will not contribute anymore to the fire.
When things have gone wrong in the past, and we've seen pictures of the fire brigade, I saw one, maybe it was in Norway or I forget where, and they literally picked up the car with a crane and put it inside a shipping container with the roof off, full of water. They literally gave it a bath, but it had to be in there for many, many days. Why does it take so long to cool down? And, well, how hot was the fire?
Especially because it has everything, let's say, on board for keeping burning. It also has the oxygen, let's say, on board. So in order to reduce the process, or to keep, let's say, the process under control, you have to release the energy or to cool down the battery. So the only or most efficient way is to put it into a water, let's say, box, as this is the most efficient way to get the heat off. And we are talking here about, let's say, more than 1,000 degree. The evaporated electrolyte gets even higher to 1,500 degrees. So every component that is in contact with these high temperatures starts immediately melting, and it just destroys and propagates through the entire vehicle, and more or less to keep really this process, let's say, or to slow down the process, put it into box of water helps here. But of course, you continuously have to cool it over a couple of days.
That long, 48 hours or days, rather than just an hour or two.
That is simply the heat transfer into the cell needs to happen. You need to cool down the cell itself. Now, we talked about before, the cell is in the module, it's in the battery pack, it's in the car. So how does the water and the cooling agent actually enter there when there's gas coming out, which is 1,000 degrees? So as soon as it comes into contact with the gas, it evaporates and it bubbles. So the water needs to find ways into the pack, into the cell, into the module, which are already burned out, and then it can creep in. So it takes quite a while actually to enter into the battery for the water and to enter the cool energy into the burning spots. So some fire brigades in testbed environments have actually created fire access guns. So they would enter with a spear into the battery from behind the rear wheel or from in front of the rear wheel, and inject the water directly into the battery in order to make that process a lot faster of entering into the hotspot.
I did hear a story once, and it makes sense now. What you just said. I heard there was a story in the news of a scrap yard or a junkyard, and there was an electric car in a crash. And everyone was fine, and then the car got shipped. It was wrecked. It was ridden off, taken either on a lorry to the junkyard, and then the next day it caught fire. And at the time I thought, well, that sounds, I don't know if I believed it or not. Like, is that true? But could that have been true then? Can it take time for that process to happen?
Most of the time, actually, it's not the time, but the moving the vehicle. So in case you have a crashed vehicle, it might have something deformed and there might not yet be a short circuit. But you transfer it onto a lorry and from the lorry back onto the junkyard, and setting it down on the asphalt might move something in there that is broken, causing a short circuit. And this short circuit then causes the cell to heat up, which will take another, quarter of an hour, 25 minutes. And then after half an hour of setting the car down from the lorry, you actually see the fire come out. So you don't think it's somehow connected to an action you did with the car, but it is.
And I think also what is another aspect here is, if you put the vehicle, let's say, away from the accident, maybe you can also damage the cooling system, which probably is still active. But if then the cooling fails, it can, of course, also cause an overheating of the battery.
If there is a fire, can any bit of the battery be salvaged or not at all?
So if there is a fire today, we do not salvage any part of the battery. There is some ideas on if you could salvage something out of used batteries like BMS systems or electrical components, but we're talking mainly about the used battery systems that saw their end of life in a healthy condition.
What are manufacturers doing, either cell makers or anyone in that supply chain of making a final battery pack? What are people doing to keep batteries safe?
There is many levels on which you can keep batteries safe. It starts on the inside of the cell to make the right electrochemical compositions of cathodes, anodes, electrolytes. It goes on around the cell in the packaging of the electrodes into the cell, what kind of safety mechanisms you can add to the cell. It then continues on the module level to have a voltage insulation, thermal runaway inhibition. When we said keep the curve flat, there is materials between the cells that can actually inhibit heat transfer or direct it in another direction. There is early warning systems on a pack level where you can, out of temperature sensors, you can predict temperature coming up or going against some safety margins. And the BMS managing the whole strain of the battery by communicating to the application what can be drawn in power from the application or what kind of fast charging you can put in. So it starts on a microscopic level and it goes all the way up into the controls of the whole vehicle.
So at every level, work is being done to make them even safer than they already are, which is incredibly safe when we look at the statistics. Accidents happen with the best will in the world. What are the various events that can cause an issue? So obviously, I understand an accident, but what else can go wrong to cause a failure?
So currently we are implementing very strict standards on the electronics and control systems like ISO 26262 functional safety, standardizing 3-level safety routines on anything that is moving or controlled inside the battery. So basically we are a lot concerned about intrusion, be it a tree or something else, another car, anything like that, or stones and rocks from underneath. We're also concerned about intrusions due to leaking cooling systems, for example. The third case, which really is an intrusion into the battery pack, is also chargers. Chargers can have very different current profiles depending on grid fluctuations. And you wouldn't believe how many different chargers are on the market, and that they, even though they're standardized, do behave differently. Makes quite a mess in the industry currently to communicate with them, make sure everything is safe while you're plugged in with your vehicle to something that can actually create over voltages, over currents to your battery.
I would just presume that all the chargers are roughly the same, but can there be a difference in charging technology then?
Not only in charging technology, but also in communication. So I think most of the chargers that don't work today are not so much the technology wrong, but the communication between the vehicle and the charger, which is standardized and fully automized, is a couple microseconds off, and that's why the vehicle won't charge correctly.
This is what people call the handshake, right?
Yes, exactly. So the handshake needs to be done correctly for the charger to start. And then there is a lot of safety implementations. So one that we were shortly dealing with is, for example, that once the charger gets the command to increase the current, how long does he have time to actually do that? How long does it take for the charger to react to this command of the vehicle? If the vehicle acknowledges it's too long, then it will shut down because it says the charger is broken. But how long is too long? Every OEM has a different opinion on how long is too long.
I think one, let's say, additional aspect also here for this is we have on one side the battery safety, which is, I think, really of interest for the driver, for the consumer, as well as for the OEM. But on the other side, when we always talk about new technology and convince people of that's very good and interesting, they also need to sell fun. And let's say long charging time is not something you can really sell really nicely. And also, when we just look at all the electric vehicles, they have a lot of, let's say, power. So you can compete with a Porsche, and it's still an electric vehicle. But there's a compromise because all these, let's say, performance targets, they also stress the battery extremely. So there is always a compromise to make a safe battery and to make a boring vehicle. And it's not only to have an accident, of course, you also have to consider that. But how to find the right trade-off between, let's say, fast charging that is really quickly, aging of the battery, because you don't want to use it only 2 years like for a cell phone, and the safety. So there's kind of a compromise you always have to find, and that's also something where you use simulation also here to play around here with the different concepts and let's say see the consequences in a quite early phase.
It's a really interesting point about longevity because this phone in my hand. I'll hold it up for the camera, but it's a podcast, so useless with audio, apart from Juergen and Wenzel seeing a picture of my son in sunglasses, which it's pretty cute, I must admit. This phone is 1 year old. In another 2 years, it's probably not going to be, it may be down to 70 or 80% if I'm quick charging it a lot, and we all use our phones a lot. But EV batteries, 10 years ago, we wondered how long they would last. And those cars that were on the road 10 years ago, many of them, okay, some of them aren't in good shape because of very hot climates and lack of thermal management in early electric cars. But largely, these EV batteries are going for much more than people assumed 5 years ago or 10 years ago. Were people pessimistic 10 years ago and they assumed the worst and actually batteries are just going for a lot longer? Or is it things like thermal management? Because obviously this mobile phone has a degree of thermal management, as in the software, the BMS would shut it down if it overheated. But that's, an electric car's a lot more sophisticated with the ability to either cool it with liquid or air cooling or all those things.
I think some of the batteries that were created 10 years ago live longer than they were expected. Some others don't. There is quite some battery products that we tried to use, and it works out, but the reasons are manifold. So you start with more robust cell chemistries like NMC 111 at the time was quite more sophisticated in terms of longevity than 811 is today, which will come to the market now. And on the other hand side, at the time when Tesla started in the Model S, they knew it was 600 to 800 cycles that it would survive. But 600 to 800 cycles with 300-400 kilometers of range is still quite a lot of cycles. So we knew at the time that batteries can do it. We knew at the time that they would live longer, 8 years or so, but nobody had a proof for it. And I guess that missing proof actually went against the people putting EVs to the market, and went in the public opinion against their assumptions that they had. Now we have proof that actually those assumptions were not that bad. I'm happy about the fact that you're stating that many of those cars live much longer than we expected.
I think also they have been quite set up quite conservative. If you come on the market with new technology, I think you don't want to fail, and therefore you put a high safety factor on it. And just if you are doing right, then they can stay much longer in operation, which finally turned out. So there was a lot of, let's say, lesson learned, and people know much more about risks and potential problems, operating conditions, and things like that. So they can make use of this know-how to develop, let's say, more advanced solutions. But yeah, it's more or less maybe also reducing here these safety factors because you know more about the batteries.
Mm. And knowing everything that we've learned so far and more to learn, the goal is always for 100% safety in everything, consumer electronics and all areas of life. But with fundamentally with the chemical process that happens in a cell, to make an EV. Can we ever be confident of getting to 100% safety?
I think we are already at this point. We just have seen at the conference at the AABC last year in November, where Nissan just presented that they have now really hundreds of thousands of cells on the market in vehicles, and without, let's say, any serious incident. So they have more or less already achieved this 100% safety goal. And again, this is, I think it's possible, but it's where you put the main focus. Is it really the safety? Then you, of course, have consequences and to maybe reduce driving range or capacity or other targets. But it's, of course, already nowadays achievable.
Let's talk a little bit about battery design and how to make them safe through design. A friend of mine had his car flooded, came above the axle, came above the wheels. by the time they'd taken the seats out and dried the car, it was a Renault Zoe, it was absolutely fine and very, very safe because the level of the water didn't go above what was called a breather valve. If it had have done, it would have been very bad news, but the water level didn't get so high. Why do batteries breathe?
Batteries do have actually quite some significant air volume inside it. And if you heat up or cool down that air volume, it changes its volume. So you would get a pressure difference between the outside and the inside. Just imagine driving out of a cold underground parking and you go into warm air around. So you would get a pressure difference between what's inside the battery and what's outside the battery. And then remember that those batteries are quite large, flat pieces under your floor. If there's a pressure difference, those covers would just start to bulge or to concave into the battery. And if they bulge, they clunk quite badly against your underfloor. You don't want to hear that. So that's why there is actually a breathing valve in there. And for the Renault, actually, there is another thing. The Zoe battery at the time was air-cooled. So it had a closed air cooling system, but it was pushing air around in the system. And so it needed an extra big breather valve because there was a very large air volume. Today, we're thinking for liquid-cooled batteries, we're thinking around 22% volume is air inside a battery at maximum. But for an air-cooled battery, it's much more.
Yes, I remember the first time I plugged my Zoe into a fast charger and the fan came on. I thought it was going to take off. It was, I hadn't heard it before. Like, what's that noise? Just the fan, air cooling the battery.
There's another, I think, important safety argument for these vents. In case of a thermal runaway, we are talking about here venting gas that is extremely hot, more than 1000 degrees, and hundreds of liters of evaporated electrolyte are released into the battery pack. So you also have to guarantee that in the case of an accident here, that this venting gas is, let's say, released in a controlled way. Not just that you release it somewhere you maybe, let's say, get problems for the passengers because it's released into the passenger cabin, or the fire brigade, let's say, is harmed because of in some areas this hot venting gas is uncontrolled released. So in case of fire or thermal runaway, these burst discs, as they are also called, are used to have a controlled release of this poisonous and toxic and burnable gas.
AVL are simulation experts. How can you simulate something like a battery failure so that then you could build in extra safety?
The funny thing is when we, let's say, started on the battery simulation, we just were not sure what kind of processes are here relevant, but it quite quickly turned out all what we have done in the past in combustion engines are in a similar way also relevant here for the batteries. So there is a heat source where you need to cool, and there is some, let's say, toxic and flammable gas that tends to burn due to, let's say, auto ignition or due to, let's say, ignition sources of hot particles or hot droplets. So it more or less is just taking all the knowledge, all the know-how in simulation of conventional combustion engines and apply this to the battery. So there is a cooling, and there is also this process of very high, let's say, velocities in the venting process.
Particularly if you are running a battery at a very high state of charge or very low state of charge, or fast charging it, for instance, there is actually a physical change that can happen inside the cell on the cathode and the interaction it has with the electrolyte. So as a battery gets older, what do you do in order to make sure that that is still safe?
You have to design it for the state of safety at end of life. So that is something that is an overarching principle in the end of the day. You make your starting point into a safe design with the cell failure analysis. And the cell failure analysis has to be at a point where the cell actually is aged. So it is under pressure. It has some vent gas already inside it, some aging gas already inside it. So your battery design is by design at the point where it's safe at the end of life. On the other hand side, your homologation tests and your standardization tests are done at the beginning of life today.
Where are we going in the future? What are the sort of cell chemistries of the future that we'll all be driving around with in our cars?
That is a good question, and I've just had it on work about technology cycles in battery cell chemistry and battery chemistry, and then the according changes into the battery inside AVL. And you can see today that there's a lot of people tackling the cobalt challenge, so getting the C out of the NMC and also out of the NCA. So we're looking at NM, nickel manganese oxide, and NMA, so nickel manganese aluminum oxide, as a next step after what's been announced by GM, for example, as NMCA. The first step that we're doing is an evolutionary step. And then there is solid electrolytes, so replacing the liquids, those organic liquids that can actually burn with the oxygens applied inside a battery cell by something that is more solid and that will oxidize, yes, but more slowly oxidize in the order of days or months. And on the other side, on the anode side, there is silithium that is making its way on the into the products. And some people are still talking about lithium metal, or are again talking about lithium metal in combination with solid electrolytes. It's still a very, let's say it's not a safety first technology for me at this point in time, but I will be happy to see the advances that we're doing in this area.
And then finally, are there any other advances apart from with the cells, but all the other things going on around the ancillaries and the management of batteries? How can we make batteries even safer in the future?
There's a lot of things going on, especially in manufacturing technologies and using advanced materials, glues, new silicons. There's a lot of technology advantages in using new electronic products like parafuses or semiconductor switches inside batteries. On the one hand side, for the efficiency of the vehicle, on the other hand side, for the safety of the vehicle. And the targets of keeping a battery 20 minutes or longer safe after the first warning is definitely something OEMs have written in their books, even though the standard only says 5 minutes.
We've learned a huge amount on this podcast, and I appreciate you telling us all the details of battery safety. Thank you very much for joining us on the podcast today.
Thank you very much.
Thank you.
Well, stay tuned for the next episode of this podcast as we dive deep into the world of charging EVs. If you want to stay switched on and fully charged on the latest with AVL, you can check them out online. Go to avl.com/electrification, and we'll catch you soon.